Kia ora, good morning everybody in my physics classes. Just looking ahead a little bit here. I'd like to move along. I'd like to revisit today Georg Ohm and his law, revisit the Scottish flag, then put the ideas for the series into maths, use the maths versions of the series ideas to find the total or the effective resistance of a circuit with resistors that are in series, a string of them. Then I will make a third video today. Look ahead to the next video, which I prove the formula for total resistance in a circuit where the resistors are in parallel. This is much harder, and you may find this proof today be a little bit trivial for some of you, but the ideas from this will actually scaffold your learning up a little bit to make the next bit easier. Alrighty, homework ahead. We've got some stuff to do when we return to school. If you want to get it done between now and then, feel free. Some have. If you don't want to because you're struggling, that's okay. It just needs to be done before the exams, which are on the 22nd of November now, not the 8th, sorry. Alrighty, we come back to the Scottish flag idea, and I've covered this. This is my little summary. I remember current and series is the same because the electrons follow the leader. The two words are same and split, and the two diagonals have got identical words on them. If we then just get rid of, fade out the parallel stuff, I want to focus on series now, and then extend that screen across. Now we come into, we move away from year 10 revision and we move into year 12 thinking. If the voltage in series is split, mathematically that means that the supply voltage is equal to the voltage across 1 plus the voltage across 2 plus the voltage across the third resistor all the way along. In other words, the voltages across all the things add up to make the supply voltage. That's what split means. For the current, the same voltage means the supply current is equal to the current through 1, which is equal to the current through 2, which is equal to the current through 3, which is just the current of the circuit. We can use that. I'm going to shrink that idea, but keep it handy. I'm also then going to move my face up out of the way, tuck it underneath there because I need the screen. Moving along, if we then start off with this first idea, the supply voltage is split between voltage 1 plus 2 plus 3. Look at the Ohm's law, where the voltage is equal to the current times the resistance. So that means that the supply current times the total resistance, that's of the whole circuit, is equal to I1 R1, because there's the supply voltage, there's the supply voltage. Voltage across 1, voltage across 1, I1 R1, I2 R2, and so on. Then we can remember that this little one in here from this little box in here, the supply voltage is this current through 1, the supply current is the current through 1, is the current through 2, is the current through 3, is the current for the whole circuit. So we can then put those in there to simplify things. We've got rid of some of these subscripts. But the nice thing is IRT is equal to I, this thing, and we can take current out. I is the word, is a symbol for current, for a common factor. And we have I times what's on the left is equal to I times what's on the right. We can then cancel, and I just use a little strike through font to get that, and we're left with this. Now I'm going to boost the size of that because that's the final thing I want. So the total resistance is equal to all of the other resistances added up, which is what's going on inside a series circuit, or a part of a big circuit that has got resistors in series. This idea may seem trivial, but we're going to use it in more complicated ideas, and if we expand on simple ideas, we can take in complicated ones. I'll do the second one later on. Thanks, gentlemen. I hope this is useful.